Hello everyone, myself Dr. Hari Shankar Singh. So far, we have studied that electrostatic fields are usually produced by static electric charges, whereas magnetostatic fields are due to motion of electric charges with uniform velocity. Or you can say static magnetic charges, that is magnetic poles. Since familiarity with the static fields provide a good background for the understanding of dynamic fields. So, we will discuss now time varying fields. In this video, I will start with the Faraday's law and later on we will discuss about the electromagnetic fields. Here is the outlines. First, we will discuss about the Faraday's law and then we will discuss about the electromagnetic fields. So let's start. In 1831, about 11 years after Ørsted discovery that a steady current produces a magnetic field, seemed logic to find out whether magnetism would produce electricity. Two scientists, Michael Faraday in London and Joseph Henry in New York, discovered that time varying magnetic field would produce an electric current. So, according to Faraday's experiment, a static magnetic field produces no current flow, but in a closed circuit, a time varying field produces an induced voltage that is called electromotive force, or simply you can call EMF, that causes a flow of current in that circuit. Thus, Faraday discovery that induced EMF, that is VEMF in volts, in any closed circuit is equal to the time rate of change of magnetic flux linkage by the circuit. Mathematically, we can write as VEMF is equal to minus d lambda by dt, where lambda is equal to n psi. So we can write as minus n d psi by dt, where n is the number of turns in the circuit and psi is the flux through each turn. The negative sign shows that the induced voltage acts in such a way as to oppose the flux producing it. Consider this electric circuit as shown in the figure, where the battery is a source of EMF. The electrochemical action of the battery results in a EMF produced field, that is basically due to the electrochemical action. And due to the accumulation of charges at the battery terminals, and electrostatic fields are induced, that is known as electrostatic field, and it is denoted by EE. And in the electrostatics, we have studied that E is related with gradient of potential. EE is equal to minus del V, and this field will also exist within the battery. So the total electric field at any point is E is equal to EF plus EE, where EF is the electrochemical action produced field and this will be 0 outside the battery, and EF and EE have the opposite direction within battery, and the direction of electrostatic fields inside the battery is opposite to that of outside, and you can clearly view from the figure. Now we integrate over the closed circuit of the previous equation. We will have line integral over path L E dot dl is equal to closed integral EF dot dl over path L plus closed integral EE dot dl over path L. And we know that closed integral EE dot dl over path L is equal to 0 because electrostatic field is conservative in nature. So finally, we will have E dot dl over path L is equal to integral from point N to point P EF dot dl. Thus, The EMF of the battery is the line integral of the EMF produced field, that is due to the electrochemical action field only. So we can write VEMF as integral from n to p EF dot dl, and this can be equal to minus integral from n to p dot dl, and this will be equal to IR because total current I is flowing in the circuit where the same current is going through the resistance R. Since EF and EE are equal but opposite within the battery as given in the figure, it may also be regarded as the potential difference Vp minus Vn within the battery open circuit terminal, because within the battery the potential difference will be existed due to the charge accumulation at the walls of the battery. So we will have potential difference as Vp minus Vn between the battery terminals. Therefore, it is important to note that we have following facts about the Faraday's law. An electrostatic field, that is EE, cannot maintain a steady current in a closed circuit. Therefore, we will have closed integral EE dot dl is equal to 0. And again, one important fact is that an EMF produced field EF is not conservative. That is, the field due to electrochemical action of the battery is non-conservative. And again, except in electrostatics, voltage and potential difference are usually not equivalent. Now, I will be giving the idea about the electromagnetic fields. I am discussing the moving conductor in a time varying field B, that is the magnetic field. A general case of single turn conducting loop moving in a time varying magnetic field, then EMF will induced, and this induced EMF, that is electromotive force, is equal to the sum of EMF due to the transformer and EMF due to the motional. So we can write total EMF as VEMF is equal to VEMF due to transformer plus VEMF due to motional. And due to the transformer, the EMF according to the Faraday law, we know that minus of surface integral del B by del T dot ds, and for the motional EMF we know as integral u cross b dot dl over path C. The induced EMF can also be given by VEMF is equal to minus d psi by dt, and this will be equal to minus d by dt closed surface integral b dot ds. That means EMF will induced due to the rate of change of magnetic fields over the closed surface. So we can apply this two formula to calculate the EMF according to the given problem. Thank you for watching this video.